back. I hope you had a good break. And we are continuing our collaboration session with the projects that are also working in the area of characterization. And this will be, first of all, the Nanomi Commons project that will be presented by Georgios Konstantopoulos from NTUA in Greece. And he will be talking about Nanomi Commons.
Thank you, Gerard, for a very nice introduction. Very interesting presentations so far. So today, in regards of Nanomi Commons project, I will present some work on characterization ontology development, aiding interoperability and reusability of characterization metadata. Unfortunately, Kostas could not join today due to personal constraints, so I will present on behalf. And the main contributors for this presentation are Gerard Goldbeck, the work package 1 leader, and Pierluigi Del Nostro. So Nomecommons is a 4 years project and works towards the harmonization of EU-wide nanomechanics for protocols development, relevant data exchange procedures across representative cases, and activities on standardization, interoperability, and data workflows are implemented in the project. Currently, the project runs in its 14th month. The consortium is consisted by 9 RTOs, 5 SMEs, and 5 players from industry, and their multidisciplinary expertise support the challenges of Nanomecommons in regards to characterization, modeling, and manufacturing. So the concept is to develop validated and harmonized nanomechanical protocols, while the nano indentation output will be validated by multiple characterization techniques such as electron microscopy, diffraction, spectroscopy, and also another key objective is the development of the CADA structure, which was developed and standardized within Oyster project in order to provide interoperability, and this is connected to the work of characterization ontologies. In Nanomecommons, we have multiple end user cases, including superhydrophobic coatings, other coatings for automotive, microelectromechanical systems, organic electronics, and cases in additive manufacturing. The methodology and the goals in Nanomecommons contain the development of data-driven representations in order to establish structure property relationships and give feedback to manufacturing, while this approach utilizes also previous knowledge, norms, and models that are already known in the knowledge base. While in addition, validation activities contain the current enrichment of characterization toolboxes, which is implemented to support benchmarking of novel industrial materials. Thus, efforts contribute to the improvement of digitalized characterization and the development of new industrial solutions for fast and intelligence materials assessment. Other technical challenges contain the development of standardized protocols of 3D and 4D high-speed and high-throughput methods for industrial characterization, while the standardization activities will ensure that high-quality data are obtained by the characterization methods. Another objective is to combine the multimodal output from specific regions of materials with and combine the different characterization output. And this is where the ontologized CADA will contribute with the knowledge management and the traceability of characterization metadata, which will be then deployed in the form of searchable and filled forms via an open innovation environment. This is important because the query sets functionality will enable the user to browse different characterization protocols to support the characterization needs of industry for the different materials types. So in this presentation, we'll put emphasis in three strategic objectives of Nanome Commons, which contain the interoperable characterization data structures, the ontology for nanomechanics and other characterization methods, as well as the open innovation platform of Nanome Commons. More specifically, in work package 1, um, first of all, the first step was to collect the completed CADA forms of the 5 industrial cases of Nanome Commons, including organic electronics, avionics and automotive, additive manufacturing, energy and chemicals. And then the system architecture was defined after several meetings in order to conceptualize knowledge which requires harmonized definition of terminology and taxonomies for both CAD and Nanome Commons database. And then what was agreed was about establishing efficient connectors between the two information management systems. And then, starting from ontology scope specification, what was performed in the first year of Norm Commons was the creation of a dedicated task group via the EMMC. The materials characterization ontology is supported and has a wider impact. The initial developments were reviewed and verified according to the EMMO principles, and very interesting indications were the output of these first meetings for the ontology design and the harmonization of taxonomies and terminology. And also the technology transfer via this meeting was enabled in regards to materials, characterization methods, manufacturing process, software and models, and the ontology work that is already in place in other projects. Um, so with this kickoff meeting that was held in December, and this task group, which is led by Gerald Goldbeck and Simon Clark, the short-term objectives are to have a community agreement on the representation of CADA, and more specifically, the concepts, workflows in ontology. Secondly, agreed taxonomies for key CADA entities, in particular of characterization methods, is another output. Collaboration is foreseen also with other relevant task groups of EMMC on these taxonomies. And thirdly, the establishment of guidelines to support consistent subdomain and application developments based on the characterization domain ontology is foreseen. In this case, the synergies are established between associated research projects, which include Oyster, Big Map, and OntoTrans. This activity by Nanome Commons led to many benefits regarding the official approval of the ontology structure and by the EMMO governance board, addressing the wider community needs about the capture of characterization knowledge. This common framework considers and supports the efficient harmonization of ongoing efforts in the field, ensuring interoperability and fair data documentation, as well as compliance with standardized CADA and the EMMO, which are being expanded in Nanome Commons. This is a schematic representation that is established for the automotive case in Nanome Commons. Here the characterization workflows indicate the knowledge that is being captured by the interoperable ontologized CADA, as well as the connection points between the characterization methods. This is the information that is being deployed then via the Nanome Commons Open Innovation Platform and the database. And what is especially the development is that in the CADA structure, what was captured was a single workflow for a single characterization, and with the ontologies, we can have the interconnection and linkages between the whole workflow that is required to follow in order to fully characterize and assess an industrial material. Um, Multiple aspects of knowledge in materials characterization protocols and workflows are captured, with a special focus to characterization methods and interconnections of metadata. The schematic workflows are enabling the following objectives: the identification of characterization taxonomies and connectors, the knowledge conceptualization, its workflow and protocol to be represented with the CADA and connected, and multiple workflows connected at the domain level by ontologizing multiple CADAs information, metadata capture, um, which, as referred previously, refers to currently one characterization technique per workflow. So in Nanome Commons, this is being expanded. Okay, when referring to nanomechanical characterization domain ontologies and mechanical testing ontology modularization, the goals are to separate the general domain from application-specific knowledge and facilitate its maintenance and gradual enrichment. Thus, mechanical ontology intends to capture multi-level information, including specific concepts of different types of mechanical testing in the modular design. Here you can see some indicative pictures related to the analysis and categorization of ontology concepts into classes and different modules. The protocol domain ontology and workflow schema are describing the characterization workflows and how they are represented, together with stages and operations interconnection via the ontology, and the linkages with the workflow representation in Grand MI. Further work will focus on workflow descriptions and establishment of interoperable workflow representations. The next step regarding the deployment and the functionalities of the open innovation environment include the improvement of existing functionalities and interface in regards to searching capabilities, user management, file upload, and online user-friendly CADA completion. The interoperable CADA development via the open innovation environment will be key for digitalization of characterization, ensuring human-machine readability, capability to search amongst the query knowledge and referring specifically to digital documentation of validated and curated characterization workflows and characterization cases. While in the next period, the open innovation environment will be enhanced and further work will be implemented in the connectors with triple store connectors with Dynamic Commons database. And this is just a glance to the form of the open innovation environment for the filling of the CADA forms. And thank you all for your attention. And I want to give acknowledgements to all Dynamic Commons partners. Thank you.
So we will have as the next speaker Marco Sebastiani from University of Roma Tre, who is going to speak about the Oyster project.
Good morning, Gerhard, and thank you for inviting me to this very interesting workshop. And so today I have to discuss about the Oyster project, and to describe you what we have achieved in the project and what we have done in terms of standardization of characterization data structures. So since the project is very close to the end, I will speak about the results that we achieved, and finally I will show you some examples on possible applications of what we have done. Okay, so Oyster is a project that is entirely focused on the use of contact mechanics to measure adhesion at multiple length scales and to link interfacial adhesion to physical chemical properties that are behind that. So practically the focus is on several industrial applications on the use of interfacial adhesion. And we develop in the project modeling tools to understand adhesion at multiple scales. We develop manufacturing processes, and then we also develop some advanced characterization methods. So we have some academic partners: Roma Tre, NTUA, University of Limerick, Politecnico di Torino, and then NPL and Fraunhofer IWM. And finally, some industrial partners, so Thales as a large company, and then some SMEs that are working in the production of materials, but also supporting the standardization process, the data management, and also the development of characterization methodologies. So the focus is surface-free energy, and here you can see a couple of applications where you can understand why controlling wettability and controlling surface energy is very important. So self-cleaning surfaces, anti-icing applications, but also applications where having a high wettability is desirable, like in case of contact lens applications. You may also know that there is one method to measure the surface energy, which is the contact angle measurements. Okay, but in Oyster, we realized that in many applications, contact angle measurements is not possible, is not desirable, and either because you have a very small area or because you need additional information, not just the wettability. And so that's why we decided to focus on the characterization manufacturing modeling triangle to develop novel characterization methods to measure adhesion and surface energy by contact mechanics. Here I can just show you a video about why sometimes you cannot use contact angle. This is a super hydrophobic surface. And in this case, you cannot even deposit a droplet. So you cannot evaluate the surface energy because you cannot perform the experiment. So that's why we wanted to develop novel characterization and modeling tools. These are just some examples on the structures that were developed by Fraunhofer. These were structures with adaptive wettability, some super hydrophobic surfaces developed by Thales, and then other companies that developed other applications. And then the main point is that we wanted to develop novel characterization and novel modeling methods to understand addition in a better way. So in particular, we developed nano indentation based and atomic force microscopy based methods to evaluate the surface energy by measuring of the addition, snap-in and pull-off forces that happen during a contact mechanics experiment. And then we developed also a series of modeling tools to understand at multiple length scales the addition phenomena. So from molecular dynamics to mesoscale to macro scale, to understand the effects of chemistry and topology on the addition in these materials that we were manufacturing. And so practically everything is based on this triangle: manufacturing, characterization, modeling. And the central engine is data science. So that's why we are talking also today, because we decided that the integration among manufacturing, characterization, and modeling must be done by developing of new ontologies for materials characterization, but also new data formats for materials characterization that can speak directly with the modeling in order to make data interoperable. I can show you quickly something we did. So here is the typical results of nano indentation addition measurements by the nano indentation, high-speed nano indentation method. We have a paper on this, and you can see that we can distinguish now by measuring the pull-off forces during these contact mechanics experiments, the addition on different materials. And as you can see that we are trying to understand at multiple length scales the effects of chemistry and topology on the surface energy of these materials. So as I told you, the central engine of the project is data science. So that's why we decided to develop this open innovation environment platform. The platform will be presented during the final meeting and of the project, and also during the dissemination workshop that will be done tomorrow. So I invite you all to participate to this dissemination workshop tomorrow. This platform practically is the basis on which was founded also the platform that is being developed inside the Nanomech Commons project. So then I would like to spend the last 5 minutes of the presentation to discuss you what we did in terms of the standardization and harmonization of characterization data. So we were initially discussing with all the people working in the project on what could be the contribution of the project on this subject. And our proposal for a strategy was to pursue the concept of an open characterization platform based on semantic footing and open standards. And so this means that we don't want to have one platform that should be adopted by all projects, because we understand that each project usually has its own platform. But we want to develop some language, some ontologies, and some standardization practices that can be applied by other platforms and in order to become interoperable. So on this basis, we know that different platforms can exist, but the objective was to make them interoperable. So we believed that the main step to start was the development and wide adoption of a novel metadata structure for characterization data, and we call it this CADA. So let's go quickly. We have already completed a CEN workshop agreement. So we have completed a CEN workshop agreement called Materials Characterization, Terminology, Metadata, and Classification. More than 60 experts participated to this CEN workshop agreement. And in this workshop agreement, we found a shared version of the characterization data structure. This is mostly the final outcome of the discussion. So you can see that we based on the MODA, so mostly this is based on the MODA, and we finally achieved the classification based on user case, experiment, raw data, and data processing. So the user case represents the sample and the environment of testing of your experiment. The experiment represents the process itself of the measurement, so the metrological chain. Then the raw data is the set of data that are directly acquired from the experiment. And finally, the data processing, which represents the process stage of data analysis. So on this basis, we prepared a series of templates that are available in the CADA form, and we finally arrived to some examples. So here is an example of a CADA for a generic nano indentation experiment. So we also have a platform, a data management DMP platform based on the CADA in Oyster, and everything is uploaded on a platform in Zenodo. So in the last 1 minute, I will show quickly an example. So because sorry, I had problems with the computer, so I lost a couple of minutes, but I think I should be done by 12. These are the 4 CADAs actually that we developed in Oyster: XPS, X-ray photoelectron spectroscopy on nanopatterned materials, surface energy analysis by nanoindentation and atomic force microscopy, and contact angle measurement. Then we also developed different modas for the modeling that we did in the project. You can see here. And everything was applied on the 4 main materials that we developed in the project. So drug-eluting implants, superhydrophobic coatings, superhydrophobic nanopatterned surfaces, and architectures with programmable wettability. So here is how it works. So you have the CADAs, you have the MODA, you select one application on one material, and you know the CADAs and the MODAs that should be applied. Then you develop everything about modeling and characterization. Sorry, I will skip the slides. Finally, you have the MODA. This is the MODA for water contact angle simulation by molecular dynamics. Then you have the CADA for surface free energy measurement by contact angle in this case. And then you make the 2 words to speak each other. So you can use the output of the modeling, which is the contact angle from molecular dynamics modeling, as the input for the characterization, and vice versa. So this is an example on how MODA and CADA can interact and can speak each other if you use a common language and that make everything interoperable. So just to say that Oyster is clearly included within the European Material Characterization Council activities, together with many other projects, and first of all, Nanomech Commons. And with that, I leave you the conclusions. Sorry for the problems, but finally I could make it on time. I hope I showed you that Oyster shows that manufacturing modeling characterization can be integrated using a common design platform. We developed this new form for characterization data structuring called CADA, and MODA and CADA can be interacting each other by doing a mutual data exchange. So interoperability is the key in this case.
So with that, we would like to move then to the next presentation, which will be on the TSMAT project. So I'd like to invite Cyril Marino, here to the stage, and please share your screen or your presentation, and looking forward to hearing about the TSMAT project.
So thanks a lot for inviting us, at least from this aspect, I mean, to present the TSMAT project. So unfortunately, about this TSMAT project, the coordinator, which is the CA of this project, and it's Fabien Perdu, cannot make it today, so I'm presenting it. So I will explain to you my role in the project later. At least this TSMAT project is a testbed for electrochemical energy storage materials. So basically here we have, of course, a website, and from the time scale of the project ends in 6 months. So the partner of this project, there is different kind of partners. So basically you have what we call the service providers. So since it's a testbed about characterization services, so basically you have service providers. So it means people that provide the service, the characterization service. So inside this, you have the CA, you have ESRF, synchrotron, so ZSW in Germany, VITO in Belgium, Tecnalia in Spain, CERT in Greece, Incor System in France. So Incor System is a company, and Semilab also, which is a company in Hungary. The rest is center, which are research center. And we have as well CERMA, so where I'm belong to. So CERMA, we are a company, and a company that provide. I don't know if you see behind me the poster, but at least we have already a company which provides services for industry and especially on electrochemical energy storage systems. So it's basically simple or standard service. So here in the project, we will have the role of single entry point. So basically where all the requests from customer might arise, and this will arrive to us. So we have these different partners here, and then after we have the partners which are mainly the service, what we call service users. So basically the customer test. So you see that you have many companies here which are providing different kind of technologies. As I was saying to you, it's about electrochemical energy storage systems. So basically, of course, you have the so-called lithium-ion batteries, the ones that are in the road now. But as of course, there is as well other kind of batteries, the old solid state batteries. You have as well the lead acid batteries, zinc air batteries, redox flow. So basically, you have a very broad pool of different technologies. So about this project, it's important to understand the spirit of it. So basically here, the role of the project is to increase, because there is a European market which is about battery, which is expected to increase a lot in the next years. And then here we need to develop, in fact, a competitive battery value chain in Europe for that. And this is why here we decided, at least Europe decided to create a platform to have all, let's say, characterization method in support to the industry. So here the idea is to provide this access to advanced characterization solution to battery industry in order to help them to develop and accelerate innovation. On the other side, of course, the partners from the project, so which are research center in battery communities, they also could benefit from it. So the different objectives are here to set up this open innovation test bed to provide efficient, and what is important to understand is that it's commercial service. This is really the goal at the end, is to provide this commercial service. To demonstrate that, of course, we are able to have an added value for the industrial problem, and of course to make it and financial sustainable in order to use it during the full time of the development. So basically, how we are going to work and how we are working is that we are having a request from the different service user, what you see here with the mouse. So you have in different kind of technology. And then after they come to us with a very definite problem. However, it's sometimes very difficult to translate it into, let's say, a scientific case. So basically, we are here to trying to discuss with a different partner to try to select what could be the right technique to solve the problem from the industry. So this is here our main goal, let's say. And of course, this needs to be done with, of course, a limited amount of time and also a limited amount of characterization technique. The goal is not to provide thousands of techniques to the customer. It doesn't need it. So here from the timeline of the project, we are, as I said to you, at the end of the project here, almost for being ready for the commercial activity. So it was set up, let's say that we develop organization at the first step, and then after here, we are testing our platform and attract new customer or new provider in order to develop it later for the future. So from commercial aspect, how it will work very briefly. So here you will have a contract that will be designed between the customer and the single entry point. So basically CERMA, the company what I belong to. And then after, inside, we will have a consortium that will run. From commercial perspective, it will be subcontracting between CERMA then and all the different service providers. And we will have, let's say, something which will be optimized for standard or non-problem. So it means that we already know, identify which kind of problem it is and which kind of solution. So we provide it. And in the same time, also for complex problem, we have also scheduled a discussion with experts for trying to solve the problem. From the data point of view, this is what I'm coming to, based on what is discussed today. It's we have a database. We'll have a database in the project that will be managed by CA. What is important to mention from the database and the data which is inside is that they still belong to the customer. It's just that we ask the customer, okay, with the data, what can we do with the data that we are going to collect? Can we disclose your data to the consortium or to public, or can we, or is you want to keep it as confidential? You will see later about this database. So I will show you the structure of this database. So basically, you have here on one side the technology which is used. So like, okay, first of course, if it's lithium-ion battery, zinc air battery, or whatever. And of course, after a sub, let's say, technology, you know that, for example, in batteries, there is different voltage which are possible. Uh, Nominal voltage, so which are linked to the material which are used inside the batteries. So here it's also called technology. Then after, we will have a unique sample ID that will be created for each sample. Okay, so this is what is mentioned here with sample ID. And then after, this sample ID will overcome different kind of techniques. So these techniques will be described in the database structure. So we'll have, there is different, technique description and technique ID, I would call it like this as well. And this technique ID, once they are performing a test on a sample, they need to produce a test ID in order to be implemented and linked to the sample ID. You can after, of course, we will also provide results through this. So this is important to understand that in the database, the goal is not to store raw data, it's to store the main results. So basically here, this is really a big difference, I would say. We are not going to store raw data, but we are going to store only main results that can be used by everybody and taken by everybody in order to think about modeling, for example, and so on. So this is very important for this. So here, the idea of the database is also to produce, some automatized result, I would say, automatized graphs and so on. So this is also what is currently developed in the platform. Now, as I said to you, what is very special is that here the idea of this platform is to become commercial and provide commercial services. So as you can imagine, in the industries, they don't want to disclose data. It's clear that most of them, they don't want, and I can understand why. However, here we have tried to find a way to convince customer to provide us some access to some data. So we will propose to them different options that you can see here, A, B, C, D, E. And then basically here, the idea of this different option is, okay, first of all, the option A, we just keep data confidential between the partner which are involved in the resolution of the request, let's say, yeah. And then after, the other member of the consortium does not have access to this. So this is basically no disclosure. After, we propose to have a partial disclosure, BC, for example, here, a partial disclosure to this to the data, and in exchange, let's say, so it means that even people who are not involved in the user case could have access to this data. However, as a counterpart, we propose to them to have a bonus price. So it means that a reduction of cost in the total order, and also to create an after-sale service to have, let's say, access to the last update, I would say. From option D, it will be a full data. I mean, they accept to disclose all data, and in exchange, we provide, I mean, like a kind of advert through our TISMAT website. And here, basically, we promote the work of in our network. We promote the work of our customer. So this is a different way that we found to convince customer, and the customer from our platform already mentioned that it could be interesting for them, depending on the work that they would like to provide us. They could select option B, C, D, for example, really depending on what kind of data they are expecting. So now, I mean, I think I'm almost on time, and I thank you again for this, and don't hesitate if you have questions or remarks.
And so now we come to the Charisma project as the next presentation. So the presenter for that will be Raquel Portela.
Hello,
And, hi,
everyone.
Good morning.
So thank you for the invitation. I'm glad to be here today to present Charisma project. So Charisma project is, the name is Characterization and Harmonization for Industrial Standardization and Advanced Materials. But what it's about is about Raman, essentially. It is a 4-year project funded with 5 million euros. It is coordinated by the Spanish National Research Council, and it has 14 partners from 9 different countries, both from academia and industry. The objective is to harmonize Raman spectroscopy. For this, we are developing algorithms and protocols for spectra acquisition and analysis. We are also developing reference master samples and theoretical spectra that will help for calibration and quantification. We are also designing specific hardware for our case studies for inline and on-site measurement. We are aiming at correlations between the obtained data and process or product descriptors, and also to develop a fair database that will be the final step for all this data. So the expected impact for us is that we will foster the industrial implementation of Raman spectroscopy, which is already widespread and increasingly used. And we hope we can help improving the business, the existing business, but also to develop new business based on Raman active nanomaterials that will face different societal changes. And for this, we have the following scheme. There is a core work packages that are going to develop models and the corresponding theoretical spectra, different kind of protocols to obtain experimental spectra, and then algorithms that will treat those data and harmonize them. And finally, this data will be stored in a database. And of course, we have work package 7 that will try to standardize the models, protocols, and algorithms. For this, we have been performing a thorough review of the existing standards, guides, and practices for Raman spectroscopy. We will publish this soon in a spectroscopy journal. It's already in press. And of course, our developments will be tested in a round robin and will be also applied in work package 6 in our demonstrators. We are aiming at 3 demonstrations in 3 different industrial environments, which are relevant. The first one for the chemical industry. We are going to control the synthesis of a nanocatalyst, which is a zeolite. We are aiming at replacing X-ray diffraction ex situ characterization by inline Raman. Then the second demonstrator is also a very interesting one related with security and authentication. We are going to apply Raman to detect nanomarkers that we are going to place in different documents. But this can be extended to different kind of value goods. And the third case study is related to the food industry, also a very big sector. We are going to monitor the quality of food through the package that is going to have an additive that helps preserving the food and is also Raman active. So these are only examples of the applicability of Raman, where harmonization can reduce the problem of the lack of interoperability that still exists in Raman. That is also more and more relevant due to the increased use of software hardware, so low resolution handheld devices, and also to adapt Raman to the Internet of Things. So our vision is that Raman at the beginning of the project is a very powerful technique, but sometimes the Raman fingerprints are encrypted and we cannot easily compare due to machine location and operator-specific artifacts. So these artifacts are generated at different levels of the Raman characterization experiments. In the user case, in the experiment, and especially also in the data processing. And data processing in Raman can be very simple or very complex depending on the application. So our approach for this is to really improve calibration, harmonize data, intervene also in the data processing to make it to preserve the information after processing. So finally, we aim at harmonization and fair databases. So for this, we are developing calibration standards. We try to standardize procedures, and then we try to easily convert our data to a universal and open format that will be stored in a database that will enable exchange, collaboration, and training of artificial intelligence prediction models, because the data are really harmonized. So for single or easy spectra, this harmonization process will allow easy comparison and identification and information extraction, but especially for bigger amount of data from different locations and different instruments, or even different stages of the life cycle of a product. We are going to make this data possible to combine to generate models, predict materials properties, and also these models that can be transferred through algorithms. And so for our harmonized Raman data, a key point is that we have to define the structure. Sometimes even when the Raman spectra are very simple, look very simple, like this one of silicon in the screen, it's not easy to universally describe it, because we have different data and metadata depending on the instrument, the user, the operating conditions, the number of digits, the data format, even the terminology is different. And if we want to read all kind of data and store it harmonized, we need a common structure. And for this, we realized that we need to harmonize also the terminology. There are many definitions of terms related to Raman spectroscopy. There's also an ISO standard that is about to appear. But yeah, we had the need to really define the terms and relations that we are using in Charisma, and we have decided to convert them to Wikidata items and properties. We have now more or less 200 terms, and this in the end will be connected to the spectra metadata. We have selected a media wiki software with a wiki-based extension because we want a user-friendly user interface. And this way, we are going to open this Wikidata to external users for contribution and for consultation. Then I'm presenting here what is our Ramankada Python script that we have designed to be able to read almost any kind of Raman spectra and be able to process it according to the most common processing techniques or tools. Also, how to plot this data, pre-treatment with cosmic ray removal, calibration, baseline separation, peak search fitting, and all these things. This work is already advanced, and the chemometric part for the use case studies is what we will deal with in the next years. The idea is that we get the metadata and raw data, and we have different methods to convert them to a log list and to process data that are going to be stored as HDF5 in our database. So our database is under development, but it's already under testing. So we have already started to upload some data. We are using an open source cloud native HSDS for HDF5 storage. And this is accessible via REST API. We are also developing for batch upload a Python based on Plumber backend workflow. And this is how the database looks like. We hope we can have it completely ready soon. We are starting to use it with our round robin data. So the database is accessible through the browser and also through API. Here you can see how it looks like with different menus to choose the metadata and to upload the data files. And here are just some examples or what is behind. So in the end, at the end of the project, our aim is that when we get Raman data, we have an application where we can just drop the data files and maybe add some metadata or some comments on this, and then we can get really harmonized data that can be easily used for database search, for model development, and combined with data across instruments, across domains, across the life cycle of a material, and that's all. I hope you find our project interesting. Thank you. I am co-coordinator of the project with Miguel Bañares, and here you have information on where to find us.
So yeah, we have to move on. The next presentation will be on the Easy Stress project. And I would like to invite the speaker, Nikolai Zangberg from Technologics. Yeah, on the stage. Nikolai.
Great. So now the video is also on. Can you hear me?
Yes, very good. Yeah.
Excellent. So for those of you who are not from the metal world, then residual stresses are the known unknown. So you know that you have residual stresses in any metallic component, and you know that they can be damaging and they can cause things to crack. They affect the strength and especially the fatigue behavior, but also corrosion resistance. But there's no really established way of measuring residual stresses in the bulk of material. So please advance. So for that reason, we proposed the Easy Stress project, which introduces these new characterization techniques that are available from neutron facilities and synchrotrons, where basically you want to move the case from an area where you do not know where the stresses are and to a case where you can actually start using the stresses, manipulating the stresses even, and being more reliable in your components. So the benefits that'll give is that the risk of failure is reduced. You save material actually, since the way you deal with stresses right now is saying we don't know what the stresses are, so we're going to add some more material so that we are sure it's not going to break. Once you know what the stresses are, you can start trimming those the thicknesses and actually save material. And finally, the time for introducing new products is quite long, since you have to undergo long testing campaigns. And instead, now you can reduce the time to market if you understand and know the stresses. So we started a little more than a year ago, and we're now starting to generate the first results. So please go to the next slide. We chose a quite industry-heavy partnership here in the consortium. So we are 2 RTOs and a university, and then we have 4 research facilities where 2 are synchrotrons and 2 are neutron facilities. Then we have a standardization body on board, and then a number of industrial partners. Some of them are very well known to you. We chose the industrial partners to cover different industrial sectors. So if you just take the next slide. Then that sort of illustrates that we have representatives from the wind energy sector and from space, from additive manufacturing, from aerospace, and from automotive in there. So the idea here is that anything we develop, it should spread into these industrial sectors. Please advance. So when we're talking about measuring residual stresses, actually there are a lot of techniques there. As I mentioned, using the synchrotron and neutrons, that's quite unique, since there you can penetrate into material and see the stresses. And when we are depicting what you can do with these techniques in terms of spatial resolution and penetration, then it's clear that synchrotrons and neutrons, they occupy a space that's not previously been accessible. That being said, of course, we need to compare quite a bit with already existing techniques. When you want to measure the stresses, you have to make some decisions. Do you have to use the same part again? Then it's okay maybe to have a destructive technique. Otherwise, you need some non-destructive techniques, which is what the synchrotron and neutron techniques can do. Then you want to see what should the resolution be, how deep do you want to go, do you want to see different orientations of the stress, and also how to get the measurement done, how long is the waiting time, what is the cost, do you just need a measurement, or do you also need sort of a whole consultancy package on top, and also which type of material can you actually handle here. So a lot of these questions go into the decision tree when deciding which technique to use. If you take the next slide, then I sort of have the overview of the different work packages we have. I'm just going to focus on the middle part, where we have a work package taking simple case components and benchmarking the different measurement techniques that I just showed on the previous slide. Benchmark these techniques against each other and validate how are the synchrotron neutron techniques performing. Then the middle section is very heavy at the research facilities, where they're developing these tools and adopting them to better meet the requests from industry. And then finally, in this, what we call work package 5, that's where we have the real industrial samples, and also how should this open innovation test bed basically be set up for the future. Now, when we're talking ontologies, I think it's quite relevant to specify that in the dialogue between the industry partners, who are mainly in work package 5, and then the facilities and academics in work package 3 and 4, it's certainly been evident that there's language barriers, and using ontologies and the charter principles is a good communication tool to have things said in a very clear way. We also, talking about languages, let's see, we're also very engaged in standardization. And I think the next slide will show some of these benchmark samples that we want to use. So basically, there's a couple of reasons why we defined these benchmark samples of this work in work package 2. So first of all, as I mentioned, we want to benchmark the different measurement techniques, and we want to do that in as simple geometries as possible. We've made these samples that are shown in the figure, and the measurements are ongoing at the moment. Basically, these different reference samples, they represent different degrees of complexity, from a very simple on the left-hand side to more complicated, being additive manufactured, welded specimens, or cast specimens. And this is also to see these techniques that we're trying to introduce, they will not be universally applicable. So we also need to know what are the limitations. And then as a final point I put there, when we start developing the standard, then we can make a reference back saying, okay, when you do this measurement, you need a calibration sample, which is looks like this. So that's also part of the reasoning. Please advance just one slide. Let's see, that's where we start on the standardization, yes. So, I mean, I put the general exclamation that standards are the language of industry, really. So it's turned out that it's a huge barrier for industry that there has not been widespread accepted standard in this area. So for that reason, it's really a focus of EasyStress to develop this standardization. I'll not go into details with these things here, but just also to clarify that once you're in the world of standards, then the clock will start ticking. So towards summer this year, we're going to submit a request to open a working group on the standards, which is called the NWIP, a new work item proposal. And then we have 1 year to finalize that work. So if you take the next slide, and it also marks the point where we go from something that's under my control as project coordinator with the partners we have, and then it's actually put out into the SEN work where the standards are being developed, where participants from all over Europe can join, which is a good thing, I think, but it's also a risky thing, since will it move in the direction that we want in the project? So that's an interesting discussion we're going to have over the next year. Please take the next slide, where I just go back to the reference sample and just highlight that part of our work will also be using these measurements that we do and comparing with modeling data. And that's also where I see a good coupling with the EMMC. In the end, at the companies, it'll be design engineers who need to use the data. So we need to be sure that wherever we measure it can go straight into the models. So that's also where this translation and ontologies is very important. Please take the next slide. Now, I skipped a couple of slides about the preliminary results from these samples, but they'll be presented in 2 weeks, I think, in a conference. So stay tuned there. In the end, I just want to highlight that we're actually doing quite a lot to try and engage and build really a community in this area. So of course we have the standard homepage, but we also have a registration form that people can join, and then they'll get invited to our events and see news from the project via our newsletters. We also have a LinkedIn page, which I guess is fairly standard as well. Then I want to highlight something that we introduced last year in this, non-physical situation we had. We introduced webinars to share knowledge in the project, and it actually turned out that these were quite popular. And when we looked at it, actually we could see they could be public. So this is now something that we are offering everybody who registers on the homepage, that they can join these webinars once. I think we have once a month. They'll start in 2 weeks again. So in my last slide, I just want to mention the 2 that we have scheduled for the moment, where we actually, so one is actually they're both given by project partners, but we have things in the agenda where we are inviting people from outside as well. So these are some of the tools we're using. If you check the next slide, I think that was the last one, exactly. So this was prepared in collaboration with our communication officer, Mark Thierry from Rayan. Thank you very much.
So we are now coming to a couple of presentations. The final two presentations will be on materials modeling marketplaces. The first one will be given by Dirk Helm from the Fraunhofer IWM about the marketplace project. Dirk, over to you.
Okay, thank you very much, Gerhard, for the kind introduction. I'm Dirk from the Fraunhofer IWM, and I present you on behalf of the Marketplace Consortium now the materials modeling marketplace for increased industrial innovations. So, oops, so some technical things. Okay, so the consortium contains on 18 partners distributed across Europe. The project runs already more than 4 years, and we are finished the project until the end of the year. And the motivation for the marketplace is that there is a need from the industry, from the society in modeling and simulation in different fields. On the one hand, for material design, on the other hand, for process design, component design, and there are more and more sustainable design questions inside. If we look to the market perspective, then we have a situation that, maybe I take my pointer, yeah. Then we have a situation that we make a feedback analysis inside the marketplace project. And if we look what the customer needs, then it's something like create, explore, interact, and execute capabilities. On the other hand, the market should provide something like broker, provider, and something to utilize something. And if you look into the market, there are already platforms available. We also heard it today in the meetings like Science Exchange, IDEX Lab, Material Square. And what is needed is something like a one-stop shop. And the marketplace in its concept has a goal to reach the level of a one-stop shop for materials modeling. What the marketplace will do is that we would like to provide an infrastructure where you can make it to a marketplace by bringing your own applications, your own workflows, your own data, and bring it to the marketplace. If we look a little bit more in details about the capabilities of the marketplace, then we have 3 key pillars. So on the one hand, the explore, the interact, and the create and execute. And for example, you should be able to search data and knowledge on the marketplace, like for example, data about materials models, software codes, and some data of materials. In addition, for the interact, you would like to get advice and support, like training, education, and also translation services, also related to OntoTrans from the topic. And with the create and execute pillar, you would like to develop and deploy something like bring your software to the App Store, use pre-configured workflows or configure workflows, use the integrated open simulation platforms like AIDA, and use integrated HPC services. In the background, there are some technologies installed, and the key concepts are the interoperability, the ontology, the variability, and the platform design and the available resources. The interoperability is for the seamless communication between the services and tools via semantic technologies. For the ontology, you must keep in mind that the marketplace needs different kind of ontologies, like for the platform management or for software and workflows. The variability allows you that you can tailor the marketplace to your own needs. And one question for the workshop was how you could interact with the marketplace. What are the interfaces? On the one hand, there's a user interface where the user can interact, but also the developers can interact with the marketplace via different kind of APIs. So for example, for the App Store, there's a marketplace API to connect software to the marketplace. On the other hand, for integrated service, we have also used REST API mainly to make these services available. If you go a little bit more into details, then of course we have these different kind of levels for the ontologies. We have the goals that we also will incorporate onto the marketplace platform multiple projects with running at the same time, like SimDome, ReaxPro, and so on. For the ontology, we based our ontologies mostly on the EMO, And for the interoperability, we have different kind of levels incorporated into the marketplace, how you the software tools and third-party tools can communicate with each other. And the highest level is really this interoperability level where we communicate via the marketplace. The technology in the background for the interoperability is realized in different ways. One way how we do it is by using the Symfony package, is a Python package to enable the interoperability between data across multiple third-party tools. You see it here in the right figure. The central element is the OSP core. There are some wrappers and the third-party tools, and you can communicate from a syntactic layer, semantic layer, and vice versa. And for the data structures, we use here also the already mentioned CUTS elements, so the common universal data structures, which are also named by Open Model, for example. Then we have different kind of ontologies needed. On the left-hand side, you see a list of ontologies which we had developed during the project. One is the expert ontology. You see some draft or some sketch of the expert ontology. If we go to some details where the expert is connected with, we see that the expert has an organization, speak a language, has some certificates, and maybe there are some contracts related to this person. Then we need ontologies for the software, the materials, the manufacturing. You see on the left-hand side. And on the right-hand side, you see some details more. Hopefully you see the pointer quite well. I know I see it also in the other place. So it's a two-screen problem. So there are different kind of ontologies you see here coming from the stakeholders, the software models, data and services. And these are all connected on different layers so that the stakeholder may be a software provider and maybe has some software. There's some documentation available, for example. And this is a very important element inside the marketplace. Then we also collaborate with the WIMP marketplace on the European Virtual Marketplace ontologies. So also the marketplace should communicate in a reasonable way to each other. There's also a connection to OntoTrans to make these communications available. And maybe the last comment on the ontology for workflows. Also here we are working on these ontologies inside the marketplace project. And in order to orchestrate the workflows we need for carried out simulations or carried out simulations between two and more simulation tools, these ontologies for workflows are very important and a key element to enable the semantic interoperability. Let us have a short view on the marketplace because the question is also how the user may interact. I already say in the background, there still are different kind of APIs defined where the developers can interact with typically. And here we have a view on the marketplace. We have the create button upper left. Then we could create different kind of knowledge items like a software, for example. In the background, Symfony and OSP core is working to realize the connections of the data. Here, for example, the software called Micros is onboarded to the marketplace with some basic informations. After you create the item, you can also go to some more details in the specifications of the software. On the other hand, an expert may be registered. Here, George, a colleague from the marketplace, from Access, register at the marketplace with some relations to materials. What you see here in this figure is also all terms coming from the ontology. And then you have the possibility, if you go to the Explore button, to make a search. And you can make a free text search or can also use these different kind of ontologies embedded in the marketplace. And for example, if you put these search items via the ontology on the marketplace, then you may find the Micros as a software and George Schmitz as an expert. And in the background, this knowledge is connected. So the expert knowledge is connected with the software and vice versa. And that's carried out via the OSP core and the Symfony technology. There's also a global search. So it's a marketplace. You can imagine there are different kind of data things realized for different kind of applications and needs. And the global search was also recently realized, and they have the possibility to make a global search over all these data sources. The workflows is also quite important because, as mentioned, you have maybe the workflow to generate one simulation. And on the other hand, you would orchestrate multiple simulation engines in a workflow. Here we have also some technique developed, and in the marketplace itself, we have different kind of use cases. These are listed here. And the use case one, for example, is a use case about additive manufacturing of superalloys. We have first some kind of laser powder bed fusion. Then there is some stress relief annealing, heat treatment for precipitation strengthening. And then we have some mechanical properties. We have here some workflow where maybe here's a sympathics tool is responsible for the melt pool dynamics. We have the micros for the grain structure evolution and some other simulation methods. And so you see we have some need for orchestration of a complex workflow between different third-party tools. And there's some technology in the background of the marketplace, also different kind of technologies. Here's one example that you have access via the marketplace front end to the workflow builder. You could use this workflow service then and also the workflow runner until you can run the simulation on the market on a computer like an HPC computer from the marketplace or any other computer anywhere. Here you see some sketch or some short video how, for example, for the melt pool dynamics, sympathics is integrated. We use here also the capabilities of the integrated AIDA Lab platform. And we can use these also to have some like of an app-like visualization. So here now an engineer could run a simulation for these additive manufacturing with the process parameters like the laser power, laser speed, and so on, and can make a prediction of the resulting microstructure via such kind of an app for carrying out these additive manufacturing use case. So that's all what I would like to say. So the marketplace project and the platform develops quite well. So hopefully we can see you soon on the real marketplace. We also make some workshop some weeks ago where we present the capabilities of the marketplace, and we will go step by step online with the marketplace, and hopefully we see you on the marketplace. Thank you very much for your attention.
Thank you. Thanks a lot. Let's now go to our final presentation, again on the marketplace. This is the sister project of marketplace called WIMP, and that's going to be presented by Daniele Marchisio from Politecnico di Torino.
All right, so thank you very much for the invitation and also for accommodating this talk at the very end of the morning session, but it was impossible for me to do it otherwise. I'm here presenting the WIMP project on behalf of our coordinator, Welky Cavalcanti. She couldn't make it today, so she asked me to deliver the presentation on her behalf. And I decided to divide basically the presentation in 4 parts, trying to address the 4 questions raised by the organizers: ontologies, workflows, interfaces, and connectors. So let me start with really a couple of words about WIMP, Virtual Materials Marketplace. As the previous project marketplace, the objective of WIMP is to create a marketplace for materials model. Of course, we have several partners, including modelers, manufacturers, translators, software owners, repository provider, and open simulation platform developers. And here you can see a picture that was taken in the last vis-a-vis meeting, which we had in February 2020 in Torino, right before the beginning of the pandemic. Right. So the objective of the project is to build a marketplace, exactly as in the as presented in the previous project. And I'll tell you a bit more about the applications and the use cases we have been working on. But I want to start with the first point, ontologies. In particular, I want to try to describe very briefly what type of ontologies were developed in VIMP and how these ontologies are handled, managed, preserved, and shared. So in collaboration with Marketplace, a number of ontologies were developed. A set of 8 different ontologies were developed, covering all aspects of the marketplace. So as you can see here on the slide, we start basically from agents and communication, validation and evaluation, file formats, computational and data services, and then we move to ontologies for training and topics, materials, modeling, translation, models and simulation, software, model variables. And then we also have upper level ontologies defining some fundamental categories, as in the EVMPO. And of course, everything is made consistent with the EMMO, the European Materials Modeling Ontology. And as I mentioned, part of this work is joint effort with the Marketplace project and the EMMC. Now, in the beginning of the project, the ontologies were contained within 2 repositories that were made available to us by Hostus, which is one of the VIMP partners. But then starting from September 2021, all the development was moved to GitLab as a public project. So here on this link, by clicking on it, you can directly access the developed ontologies. Of course, GitLab allows to do version control, create issues, handle merge requests, labeling, and defining different releases. And then also some of these final ontologies were also posted on the MAT portal, which is a web-based a website based on the bio portal. So by clicking on this, you can see the very same ontologies on this portal, in which you can also have additional features such as graphical visualizations of ontologies, annotation, and mappings. Very simple example, for example, the translation process and how it is defined through these ontologies. There are ontologies defining the business case, the industrial case, the translation case, and then of course the use case. All these go into the application case, which then define a solution for the problem, which is a simulation. And so we have, following the MODA description, a description of the model, the solver, and the processors. And as I mentioned, all these ontologies are available at the links that I showed before. In the process of preparing these ontologies, we identified a number of issues and a number of things that should be handled in the future. In terms of interoperability, of course, semantics is an important part of the solution, but syntactics also is important. So with syntactics here, we refer to the technical implementations and the constraints they carry. And in terms of issues, I highlighted these 2, which are the 2 most important in our view: identifying suitable levels of details for the descriptions, and also the difficulty in combining consensus with a wider field and development time constraints. If you want to learn more about the VIMP ontologies, you can refer to these 2 documents. Most of the work for the ontologies was done by Silvia Chiacchiera and Martin Orsch, who are part of the STFC in the UK, which is one of the partner of the project. In terms of workflows, how workflows are represented, managed, and applied in the project, VIMP is in theory agnostic, but of course there is a specific flavor. We focus on models for soft matter. So we looked into models to describe 4 different use cases provided by 3 industrial partners: Unilever, Continental, and High-Tech. So we have models for describing the production process of food emulsions, workflows for describing the production process of personal care fluids, which involve structured fluids, production processes for polymer composites, and corrosion inhibitors. So all these models are a combination of different, all these workflows are a combination of different models, and these models are connected to each other using an open simulation platform. So within the project, we have mainly focused on the Salome platform, which fulfills most of the requirements of the MMC in terms of what is an open simulation platform. So Salome is open source. By clicking on this link, you can download it and install it locally. It has been developed by EDF, a partner of the project, to connect different modeling tools. Code Saturn and Neptune CFD are 2 of them. And of course, besides allowing the linking and coupling of the models, it also contains some generic functions useful in numerical simulations, such as 3D modeling, computation scheduling, and complex data processing. Within the project, we mainly built different workflows, all including molecular dynamics, some form of coarse-grained molecular dynamics. In particular, we looked at dissipative particle dynamics and lattice-Boltzmann simulations, and then continuum models, mainly computational fluid dynamics and discrete element models. So to link this with Salome, and here you can see a very simple example referring to the emulsion workflow. You basically need to link these 2 tools. So in this case, we have a DPT code, which predicts a property of this soft system, the interfacial tension between the 2 phases. And then this information is passed to a CFD code that predicts instead the evolution of the droplets constituting the emulsion. Of course, the codes need to be put inside the wrapper, and the wrapper handles the communication between the code and the platform. And then, of course, there is also a mapper that in some cases is a very simple operation. In some other cases, it is something more complex. And then the information is passed to the next code. So the wrappers are in this context developed by following this common data model, which is basically a way to define all the variables that are exchanged. And of course, within the project, we tried to have some degree of compatibility with this common data model, which was already existing, and the ontologies developed in the project. The common data model can be adapted, and the wrapper can be built by using this YAX technology, which is developed by EDF in the context of Salome. So I don't have time to the details of this. To give you an idea of the user interface, this is how a typical workflow looks like as it is when it is handled by Salome. This is another example. This is a GROMAC simulation with the different steps of the simulation, a molecular dynamics simulation run with GROMACs for the continental workflow. So these different nodes corresponds to different parts of the calculation, and then you have these arrows, which are almost automatically generated if the information is passed by referring to the variables defined in the common data model. We have also been working on containers, Docker containers, to basically wrap the simulation and exploit it on HPC facilities. So here you can see the list of the software that for the moment are being wrapped inside this container, and you can follow the progress of the work by clicking on this link. Very last point, interfaces and connectors, how these different sources of information are connected and what type of interface the users have to deal with. Data is handled in WIMP using the Zontal space, which was developed by Ostus. So basically, it is constituted by three elements: a submission information package, where the data record is put inside the database. Then there is an archival information package handling the information, and then a dissemination information package to extract the information. Of course, there are a number of features related to searching the information, and also interfaces to explore and browse what is contained. In terms of data structure, we have been focusing on challenges, computational resources, data sets, knowledge, people. And in terms of interfaces, the main interface is a web-based interface. So here you can see a typical interface for manual data ingest. And here you can see the the different categories I mentioned before: challenges, computational resources, data sets, knowledge, people, etc. And these are the type of interfaces that the users have to deal with, for example, to upload a piece of software or a piece of training material as a book. Since I'm running out of time, I think I can just close it here. Thank you very much, and I'll be happy to take any question you might have.